on. And slide engaged. All right. There are a few announcements. Some of these you've heard. I'll try to go through them quickly if we have. Too late in this one. Well, unless you really want to, you can. It's going to be hard to do anyway. I don't know why they do this, but they do. The office, they send out an email at 9 this morning for something that's happening at 11 this morning, and then 1 o'clock this afternoon. If they just sent it out last week, you would have had a chance to do it, but maybe they couldn't get it arranged till then. But join the Office of Student Financial Services and our guest, Ms. Penny Sumner, for an observance of Constitution Day today on both campuses. It was 11 o'clock this morning on this campus in the faculty staff dining room, and 1 o'clock this afternoon in the new Student Success Center auditorium over on the Birmingham West Campus. So if you left now, you might get there in time to do the thing. I'm not suggesting you do that. Okay? Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. I wish mythology and mathematics did not have been put next to each other. Okay, never mind. Now this is something that is pretty important happening this evening. The Birmingham Holocaust Education Center has graciously loaned the Darkness into Life Alabama Holocaust Survivors Through Photography and Art exhibit to Lawson State Community College Library. The sensitive exhibit of photography turned through bold and thought-provoking art offers a special glimpse into the private memories of 20 Holocaust survivors living in Alabama. This collection reveals stories of childhood's past, stolen family and friends, despair and sadness, cruelty beyond belief, and then stories of bravery, the joy of liberation, and their new lives in Alabama. The exhibit will be on display, started on the Birmingham Library, which is on the West Campus, started September the 4th, and will run through, I think it's next Monday, is it? September 23rd. But here's the important part. That's important. But Esther Levy, daughter of Toby Komornik Gerson, will speak about her mother's personal experiences as a Holocaust survivor. This event will take place this evening, today, September 16th, 2019, 5:30 in the ACAT Technology Theater. That's the next to the newest building on the Birmingham West Campus, the one that sits down sort of in a corner. It has a slanted green roof on it, one of the few buildings over there that has doesn't have a flat roof. Okay, that starts at 5:30, but light refreshments will be served beginning at 5. Several exhibit pieces will be on display for this event, so you can look at those before in that 5:30 time frame or after it's over. So please join us at Lawson State Community College, blah, blah, blah. So this is open to the public, by the way. So please, if you have friends, family members, anyone would like to see this, it should be very moving, a real special time. I meant to carry this out. I'll try to get it this afternoon. The Federal Reserve would like to invite you to watch an Exploring Careers in Economics, 10:30 Eastern Time, that's 9:30 Central Time, on October 11th. So that's coming up in the future. During the event, students will hear from and engage with Federal Reserve staff and research assistants, organized to broaden awareness of careers in economics and further develop a diverse pool of talent interested in the field. Exploring Careers in Economics will offer students a chance to learn about and discuss opportunities in economics generally and learn about career paths in the Federal Reserve. That's a live event, October 11th. Okay, it has all the details about how you can get to it, or you can get more information. And this will probably be the last time I'll be reading these, because I'm going to give these to Mr. Armbruster, who's in charge of business department here, for him to give to the economics instructor so she can pass them to the students in her classes. And this is the only copy I have. So if you're interested in getting more information from it, here it is. The other is the College Fed Challenge competition, in which teams act as members of the Federal Open Market Committee and present their monetary policy recommendations to a panel of judges. And the finals are hosted by the Board of Governors of the Federal Reserve. And team members will get to meet Fed Chair Jerome Powell, if he's still in office then. Yeah, I don't know. Okay, if you're blah blah. And so, more information on that. Here is one about the College Fed Challenge, websites, other information there. Here's one about exploring careers in economics. That's the one I just read to you. And then the last one is the NCAS NASA Community College Aerospace Scholars Program. Their deadline is October 16th. So both of those are coming up next month. If you want to see any of those, feel free to take a look after class or whenever. All right. Any questions on anything we've covered so far?
I have a question.
Okay.
I'll wait to the end of the class. You don't want to hold class right now.
Well, now if it's pressure in mind.
12 Section 2.
Okay.
Exhibit 3.
Is which?
12.2.
Yeah, 12.2.
And then Exhibit 3.
Problem 3, is that what you said?
Yeah, but I got Exhibit 3.
Okay. My hearing's bad. I haven't quite made out what you said yet.
I said Exhibit 3.
Exhibit 3. That would be example 3?
Yeah, exactly.
Oh, okay, got it. Okay, on page 830?
I don't know what page.
Oh, okay. Is finding intervals on which a curve is smooth? Is that?
Well, it says you get the vector R of T equals Ti plus T squared J.
Okay.
And you want to get the derivative of that.
Wait.
Prime, which would be I plus 2.
Okay, I'm not on example 3. Let me see if I can find it. Ti plus T squared plus 2J?
Yeah.
Okay, yeah, that's example 1. Okay.
Is that the one that we're going to get the slope?
Right, okay.
Okay, what I was concerned about is trying to be arbitrarily pick the best parameterized equation. Why do you pick x equals t? I know it's an easy way to do it. What was the rationale behind it?
Okay. Let me.
That's one, and then he's got the curve drawn in the 2-dimensional. We're supposed to talk about 3 dimensions.
Okay. Yeah. Let me use the white space here. I'll try to come back to where I need to be. Well, I can't get my pen to work.
No, that's not the.
No, I know it's not the right one, but I'm trying to get just some white space I can work on. Is this the one? For the vector value function, R of t is equal to Ti plus T squared plus 2J. Is that the one?
Yeah.
Find R prime. Okay, so let's first do that. What would that be?
Just 1 or just I.
Yep, I
Plus 2t.
plus 2T
J.
j. Got it. Okay. Find r prime. Then sketch the plane curve represented by r of t. So they're just doing a plane curve here. The next example is a three-dimensional. So they're starting with the two-dimensional curve and then moving to three. That was part of your question. Yeah, okay. They just started with the example 1 was 2-dimension, example 2 will be 3-dimension. Okay? So I think that's the only reason they did that. Okay, then sketch a plane curve represented by r of t and the graphs of r of 1 and r prime of 1. Now, was part of your question why they chose 1 or something?
Parameterize the equation with x is equal to t.
Okay, I missed that. Well, let's first do, then sketch the plane curve represented by r of t. Okay. I'm cheating and looking at their answer to see how to draw my graph. Okay, so we'll do 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. I don't think we'll need any this high, but I'll go with it. Okay. Now, sketch the plane curve represented by r of t. Okay, so let's now look at just the r of t. Don't worry about r prime yet. R of t. Pick a value t, any value t. 0, okay. So t is equal to 0, then you'd have 0i, so that's neither going right nor left. You're somewhere on the y-axis, and then when you put a 0 in for the second part, you get 2j. So that puts you right here. There's your first point, right? Okay, then pick t equal 1. That would be I plus 3j. So 1 on I, 3 on j. So that would be right here. Okay? T is equal to 2. That would be 2i plus 4j. So 2i, 4j. Is that right? Yeah. Yeah. That's going to be a parabola, right? That doesn't seem right, though, there.
Well, see, I looked at that, and then I looked at the other thing where you got y is equal to 2 x squared.
Yeah. What is not right about this picture? Oh, that's 6j. That's it. It's 4. 2 squared is 4 plus 2 is 6. I knew that didn't look right. That's 6j. 2i plus 6j. 1, 2, 3, 4, 5, 6. There, that's better. And then 3i would be 11j, and I think that's all scale. 7, 8, and 8. So it would be like this. Okay? Now, if you picked a negative 1, that would be negative I plus 3j, so that would be right here, and then negative 2 and 6 would be here, and then that goes off scale. So there's your parabola, complete a parabola. But this has an arrow on it. It's not just a parabola, it's a parabola going from left to right, because you put your arrow in the direction from increasing t's. So here it's negative, negative, 0, plus 1, 2, 3. So increasing t, that gets in that direction. Okay. And the graphs of r of 1 and r prime of 1. Well, for r of 1, what they mean is just draw the vector r of 1, and that's what we already calculated, be I plus 3j. Well, that vector, that would be this vector right here. This would be r of 1. It's a vector. When t is equal to 1, that would be r of 1. Okay. And then it said r prime of 1. Well, if you put a 1 in here, you get r prime of 1 is equal to I plus 2j. Okay. But the r is drawn always from the origin. Okay? The r prime you usually do from the point 1, 1, 3. You know, when r is equal to 1, you usually draw it from that point. Now, they didn't specify, I don't think, that you were supposed to do that. If you had drawn it down here, this would have been perfectly correct. 1 plus 2j would have been right here. That would have been r prime of 1. But usually you draw this from the point where, and they may have mentioned this before, where if you read on the bottom of the previous page, right before Theorem 12, it said you can see from figure 12.8 that r prime is a vector tangent to the curve given by r of t. Okay, that's so, and pointing in the direction of increasing r values. So they don't specifically say, but the implication is take this vector and draw it exactly the same. In other words, go 1 to the right and 2 up from this point. And that would be that vector. Always, and this is also r prime of 1. It's just not drawn from standard position, but from the point of 1, 2 that you got here. No, here. No, yeah. 1, 3, sorry. 1, 3. You draw it from that point. Now, my figure is pretty ugly, but you see that shows that it is tangent. Down here, you can't tell that it's tangent or not. You know, if you put it there, then it at least appears to be tangent at that point. And it's got to be. It will be.
Yeah, but see, I'm used to saying tangents like in the plane is a single number.
What's that?
Like tangent in the plane would be
Right.
a single number.
Right.
Okay, but I would expect in 3-dimension two numbers.
Right.
X and then a dy dx.
Right.
As a function. But here, what I'm trying to say, he says, what's the r prime t at that point? I'm trying to. Well, I got the slope 2, but where I got it from was substitute y,
Right.
t squared y.
Yeah. Right. When you take the derivative of this, you get that.
And then just put 1 in there. You know the slope's going
Yeah.
to 2.
Yeah, and that would be 1 plus 2, yeah, 1, 2. Which, if you drew it like you did this one, this one, that would have been down here. But it doesn't really do a lot of good to put a derivative function down here. Your original function, yeah, it makes sense. That points to where that point is. But then you take your derivative and plot it from that point, 1 to the right and 2 up from there. And that gives you, then, at least it looks like, and it is supposed to be tangent there. But there's nothing in here that said you had to do that, but that's what their intention was. Let's see. Didn't sketch the thing, and the graphs of that and that. Now, nothing they said before said you had to do that that I can recall, but it's just typically where they do it from. They draw the derivative vector from the point that where the other one terminates. And it just sort of makes more sense then, because then you see it's tangent there. this one, the function gets you to that point, and then the derivative shows you where it goes from there, in what direction, tangent to it. Is that what you were saying?
Okay. Well, I was still trying to figure out why you if I was the wrong thing. They doing the parameterized equation with the two-dimensional. They took x is equal to t.
Yeah, okay. Okay, now I think I understand what you're saying. If you had...
But why did you pick x is equal to t? Because we always, like the stuff we always say, pick the most complicated when you want to do substitution.
Oh, okay. Well, that's an integration when you're doing... and we're not integrating anything here. We're just basically doing what they tell us to, is taking this and taking its derivative, figuring out what this is, drawing that from the origins there, and then draw this one at 1, but start it where this one ends, start this at that point and go from there. And that's what you're doing now. Yeah, if you're doing this parameterization, you'd have x, or y is equal to x squared plus 2, and that sure enough is your parabola there. Yeah, and they weren't interested in that at this point, except that helps you see, yeah, that is your graph elevated 2 places, you know, it's a vertical shift 2 up, standard. And that's how I knew that point right there wasn't in the right place. It should have been up there. That's how it was calculated there. But after that, you don't take your derivative of that function. You take it of the original r. If you had tried to take the derivative of y is equal to x squared plus 2, you just get dy dx is equal to 2x. And if that's what you're saying, yeah. Yeah.
And that's what I did. So.
Yeah, but yeah, they were wanting you to take it of this one, not of the parameterized, whatever they call that, the function, but take it of the R functions and do them this way.
Yeah, I did.
Yeah.
I was just blind. Okay, let's move on.
Okay, were there others?
No, that's
okay. All right. Okay. So where we left off last time, I have to go back to it. Let me clear this off the screen because it'll be in our way later. Do you need it any longer?
No.
No, okay. So let's go back to where we were. I think this is where it was, wasn't it? Yeah. I think this is the slide we left off with last time. I think we did that one. So this is where we left off. Note that, okay, let's go back to this one. As delta t approaches 0, the direction of the vector PQ, this is going back to the earlier things, this thing here, remember here's a vector PQ, and then as you get smaller and smaller delta t's, that's, they don't show what delta t is, but as delta t gets shorter, then your curve, the Q point comes closer and closer to the P. That's what they're showing here. So your, see, the delta t is going to 0 as you go that way. Your delta r is this vector here, because there's r of t plus delta t, so this is your delta r, and those are getting shorter and shorter. Well, I say shorter, they are, but until you hit this one, and what they've done there is then divided by delta t. They don't show that here, they show the velocity vector. Well, this is just the difference vector here, not the velocity vector. If they had divided by your delta t's here, these would have been a variety of lengths. It's hard to say exactly what lengths they were, but that's why they're getting shorter, but delta t divided by delta r divided by delta t. As the delta t gets smaller, the delta r actually, it makes the overall thing grow. And that's the velocity vector at time t, not at this time or any time in between, but right there. That is the limit. And that's what they're trying to show here. As the delta t goes to 0, this approaches the velocity vector. And says, note that this is the same limit used to define r prime of t. So the direction of r prime of t gives the direction of motion at time t. Moreover, the magnitude of that velocity vector, which is what we're calling that, do that in the magnitude, that would be x prime of ti plus y prime of tj, that's the derivative. Take the magnitude of that, that's the square root of x prime t squared plus y prime t squared. That gives the speed of the object at any time t. So your velocity vector, number one, is a vector, okay? It has an x component and a y component. And the magnitude of that, which is what that gives you, is the speed. Now remember, magnitudes are never negative. It could be 0, but can never be anything but positive, and that is only positive, okay? Magnitudes have no direction. This is the magnitude, it's a vector inside here, but the magnitude when we're only focusing on the length of that vector, and that's exactly what this gives you, and that's the speed of the object, okay? Whereas velocity vector could be this way in x and let's see, that way in x and this way in y, so it can be a number that looks negative, but its velocity, its speed, is always going to be a positive quantity, unless both of those vectors are 0. Both of those derivatives are 0, and then it would be 0 as a minimum. So that's how we define speed. In everyday English, speed and velocity, we interchange them as if they're the same thing. In calculus and in physics, speed is a magnitude of your velocity vector. Velocity is understood to be a vector with direction. Take the magnitude of that, and that's what gives you the speed. Speeds are always non-negative. Velocities can be in any direction that vector turns out to be. So, similar to how r prime is used to find velocity, we can use r double prime to find acceleration, because the time rate of change of your velocity is your acceleration. It's also a vector quantity. And here's the definition of velocity and acceleration. If x and y are twice differentiable functions, got to be in order to take the derivatives twice, of times t, and r is a vector valued function given by r of t is equal to x of ti plus y of tj, then the velocity vector, acceleration vector, and the speed at time t are as follows. Velocity vector is v of t, is r prime of t, which is x prime of ti plus y prime of tj. Now let's jump down to speed. Magnitude of that would be the square root of this one squared plus that one squared. That's going to be a scalar number, not a vector. Scalar number, there's no i's and j's in that. Scalar number, non-negative scalar number, and that would be your speed. Your acceleration is take the derivative of each of these, x double prime of t, I plus y double prime of t, j. There's your acceleration vector. It's also a vector. We talk about its magnitude, but people usually don't. Okay? It's usually not as of much interest as the speed is. Make sense? Now, 3 dimension, just add a k, okay? And all these work out just the same. You need a z of tk, z prime of tk, and z double prime of tk. Okay. Now, for motion along a space curve, 3-dimensional, that's what I hope to say, definitions are very similar. Your r of t is x of ti plus y of tj plus z of tk. And you have the following velocity vector, be the first derivative of this, which is x prime of ti plus y prime of tj plus d prime of tk. Jumping down to the speed, the magnitude of this vector is the square root of this one squared plus that one squared plus that one squared. Again, a scalar quantity and a non-zero quantity. No components, vector components at all. Go back to this and take a second derivative. It's double prime I, y double prime j, and z double prime k. That's the acceleration vector. And again, we usually don't focus too much on magnitude of acceleration. You could, there's nothing wrong with it, but we don't have a special name for it, like speed is the magnitude of your velocity. All right, so here's example 1, page 837. Find first the velocity vector, then the speed, then the acceleration vector for a particle that moves along the plane curve C described by this. So the first thing is velocity vector. What would that be? I'll go on and write it as v of t, and what is it by definition? R prime of t, which would then be what? Got it? Minus perfect. Okay. Next, let's do it speed. And they don't really have a good name for speed. They just write it speed. I'm really tempted to do S of t, but later we'll see S stands for arc length, as you probably already remember. So it's not a good thing to use S, because then it's really hard to distinguish that from arc length. So that's not the same thing. So speed, I'll just write it out, speed. And it is a function of time, so you could put of t, but what would it be? T over 2 plus sine squared t over 2. Anyone know what that is? It's going to be 1. Okay? Anytime something's following a strictly sinusoidal components of vectors, sines, cosines, and they're identically the same except for the trig function, that's going to turn out a speed of 1. Just happens to be that way. Okay? How about the acceleration vector? Acceleration vector is also known as the first derivative of the velocity vector, which is also known as the second derivative of the displacement vector. And what would that be?
1/2.
Negative 1/2 sine of t over 2 I minus 1/2 j. Okay. Now, what do you notice about that? Because, and by the way, whenever you have this kind of thing, you got circular motion. Okay? This happens to start when t is equal to 0 for 0 of x, but a 1 for y, 2 for y. Okay? And then, as you increase this, the sine's getting larger, but cosine's getting smaller, so that's going in the clockwise direction. Whereas if you had reversed those two, that would have been counterclockwise. So this is turning in the clockwise direction of radius 1, radius 2, because that's that. So it's moving in circular motion, so its speed is a single unit, 1. But its acceleration is exactly opposite this, and 1/4 of the magnitude. Okay? So its inward pointing always, whereas these vectors are pointing out, making a circular path. These are pointing inward, which is your centripetal acceleration, pulling it in with x and y. It's exactly the opposite of those values. There your x is out and the y is out. Here the x's and y's are both in. Okay. Let's see how they deal with it. I think I'm going to need to erase to see it easily. Yeah, your v of t, which is r prime of t, is just simply, as we said, cosine t over 2I plus sine t over 2j, or minus sine t over 2j. Okay? Your magnitude of that velocity vector is this, which happens to be what? Because it's the sine squared of the same thing plus cosine squared of the same thing plus sine squared of the same thing. That's always going to be 1. Okay. And your acceleration vector is the first derivative of your velocity vector, which is the second derivative of the displacement vector, and that turns out being minus 1/2 sine of t over 2 minus 1/2 cosine t over 2. Okay. Thought they were going to show the figure, but they didn't. Sorry about that. It's in your book. The acceleration vector is always, on circular motion, always pointing toward the center, whereas your displacement vector is usually pointing away from the center. Okay. Projectile motion is a couple pages away, so we need to move back and do example 2. Happened again that I did not drink enough fluid at lunch, so I'm getting awfully dry, but we'll manage. Okay, we've just gotten started. So sketch the path of an object moving along a plane curve, so again in the plane, given by r of t, the vector r of t is equal to t squared minus 4I plus tj. Okay, so it says first sketch the path of an object moving along that plane curve. So since it's a plane curve, we can sketch that on a plane. Now, I don't know how you like to do it. Frankly, I just pick a T and start plotting points. If you wanted to, this would be fairly easy to do the way Bill was doing it, combining your parameterized curves into an XY curve. Yeah, that keeps me from making a few mistakes anyway. We'll see. Give me a T. 0, I like it. Okay, and what's your I component then? So minus 4 and 0 j. So there's your first point. Okay, let me pick a few. Okay, we won't need that many. Give me another T. Pick an easy one. 1. Okay. What is your I component then? -3. What's your J component? 1. Okay. So -3 on I on the X component and 1 on the J component. Right there. Okay. Next. -1, is that what you said? Okay. Okay, so let me at least draw something here and indicate that's the direction we're going. Okay, when you do t is equal to -1, what do you get? Yeah, you get -3 again for your x component and 1 for your y component. But since that's to the left of 1, our curve is still moving in that direction. Okay, still moving that way. T is equal to -1, 0, 1. Okay, give me another t. 2. Okay, you're yeah, 0i plus 2j. 0i plus 2j is up here, and if we had done a -2, it'd still be 0i, but this time minus 2j, so that would have been down here. So again, your curve is doing something like this, and something, yuck, I can't draw worth this. So it looks like, and it is, a sideways parabola. Okay? Let's do one more. T is equal to 3. 5 on the x. 1, 2, 3, 4, 5. And now negative or positive 3 on the j. All right. And on the other one, minus. Same thing, except you're down here. If I can find where I am there. Okay. So again, you're going like this and going like that. So you are heading in the right direction. Okay. I think that's enough of a curve. I think you can see it coming from this direction, going in that direction. Okay. Then find the velocity and acceleration vectors when t is equal to 0 and t is equal to 2. All right. Now, when you're finding velocity and acceleration vectors, integrate the function first, then plug in. Don't plug in and then integrate or differentiate. You're always going to get 0 then, because once you plug in, you just got numbers. So take a derivative first. So the r prime of t is also called v of t, and what would that be? 2t I plus j. Okay. All right, we'll just leave that like that. Oh, wait. Let's go and do the calculation for the other one first. R double prime of t, which is v prime of t, which is a of t, is what? 2i, and that's all, folks, right? All right. Now, let's plug in first when t is equal to 0 and 2. I couldn't find that. Okay. R prime of 0 is equal to j. All right. Where is it t is equal to 0? Oh, it's right there. And what's the derivative there? Oh, I didn't do that right. Yeah, no, it's just j. All right. Just wait a moment here. Oh, wait, no, I'm sorry. You plug in T, that's right. No, I'm sorry. When T is equal to 0, you're right here. Okay, I was over here. Okay, that's where I was wrong. When T is equal to 0, here's where you are. Okay, and then evaluate your, when T is equal to 0, your velocity vector is 1j. There is r prime of 0. Okay? And sure enough, that's where you're heading. Your curve, you're moving along this curve this way, and at this point, you've only got a vertical direction. You've turned the corner, you're no longer heading this way, you're not quite heading that way yet, so your velocity is straight up. Okay. T is equal to 0. Okay, let's do the same thing for the acceleration. A of 0, which is r double prime of 0. And what is it? 2i. So that's just 2i. Same as it was everywhere. And where is that? That's in this direction. Okay? One thing to note here, at least there, these are perpendicular to each other. Okay? See later that won't always be the case, but it will be. So you have a pretty great acceleration here. Well, think about that. When you're driving down the road and you're making a pretty sharp turn, when you're turning just ever so slightly here, there's no squealing tires or anything else. You're just going along. But then when you turn that sharply at a decent rate of speed, you're probably going to, you've got to be exerting a lot of direction to get it to turn that sharply. Here, not so much. But here, you've got to be really accelerating toward the center of the circle to affect that change in velocity. Okay? So let's go to r prime at, or was it 2? Yeah, t is equal to 2. Well, at t equal 2, that's where we are. Now I'm at the right place. I jumped the gun on it. And what is your r prime at 2? 4i plus j. Okay? Well, that's 1, 2, 3, 4, 1. Okay? So it's, yeah, I can't draw well at all. There is your velocity. You're speeding along there now, and I mean very, very close to being along that curve. Okay? That's your direction. What is your acceleration vector then? Is equal to what? 2i again. Okay? Always 2i. Well, here, 2i is in this direction here again. Okay? I can't get my pen to write. That's a pretty ugly. This is your acceleration vector here. This is your velocity vector here. Obviously, those are not perpendicular to each other. So don't think velocities and acceleration are always. Only on circles are things that can be approximated by a circle. That is a very good representation of a circle, just like this. So since that motion is the same here. Now there is a circle you could do here, but it's a huge circle that would give you that. We'll talk about that later. It's called a occluded circle or something like that, which, I mean, that's such a huge diameter. We won't get into that here, but that is. But the that shouldn't be heading down there. That should be flat after all. That's horizontal. 2i is always This one's slowing down at the rate of 2I. This is turning you at the rate of 2I, and this is speeding you along at the rate of 2I, increasing your velocity. And that's why this vector, your velocity vector here, was this way, and it's being changed as you go because your acceleration vector is always 2I. So that's what constantly is pulling this. It's curving it in here, curving it in there, curving it in there, always curving it downward as you go. Because the acceleration vector is that constant 2I. And by the way, when the acceleration is constant, as we have here, 2I, that means you have what they call uniform motion. And you don't need that here, but you will in physics. And parabolic motion is uniform motion. Okay. Now, can't see much more I can do on that one. That was example 2. Let's clear this unless you have a question and move to example 3. Any questions? Now, example 3 is one of these that you can go to larsoncalculus.com and get an interactive version of this type of example. And from what I understand from that, you can actually kind of interact with the video that you've got there. Now, how they do that, I don't know. Maybe it just asks you questions and tells you whether it got it right or not. Not a person on the other end. It's just set up to do that, which is, I think, fairly incredible. Okay. So here is vector and acceleration vectors in space. So you've got 3 dimensions. It says, sketch the path of an object moving along the space curve C given by this R of t, ti plus, is that a t cubed? I think it is. Plus t cubed j plus 3tk. All right. Now this is only good for t greater than or equal to 0. All right. No reason why they tell you that now. But it's perfectly fine to do. Okay? It says sketch the path of that object moving along that space curve C given by that thing. I don't like this, but I'll try to do it. Here's your z-axis, your y-axis, and your x-axis. Okay. T greater than or equal to 0. So let's just pick a few. Let's pick t equal 0. Where are you? Okay, you're at the origin. 0, 0, 0. 0i, 0j, 0k. Excuse me. So let's see what happens when t goes to 1. Okay. Is that what? Let me see. Okay. What you just gave me is this position vector at 1, right? And you said that's I plus j plus k. Oh, 3k. Okay. Now that's a position vector. That's not, oh yeah, we're sketching, I'm sorry, I would have jumped on to the next part. So where would that be? 1 on I, 1 on J, and 3 on K. 1, 2, 3. So it would be somewhere, goodness, I can't draw these worth anything. All right, let's just 1, 1, 3. Something like this. In 3 space is so hard to do. This is coming out of the board this way. And you can't tell that. I probably don't have it quite long enough this way. But you see, you draw this one parallel here, this one parallel there. So here would be the base, and then you go up 3. That's probably a better way to do it. Let's try to get that in the right place and go up 1, 2, 3. Okay, so maybe up to there. Okay, that feels better anyway. Okay, but it's coming out into the first octant here slightly, but going mostly northward. Okay, to Z. I hate drawing these. And that's just the first point. I probably shouldn't have even put that in yet, the line there. In fact, let me take it out. Hi! Why is that doing that? Trying to get my eraser that way. That time it took. Okay, we'll just go to this point right here. Okay, so there's the first point. The next point, t equal 2, that would be 2 here, 2 here, and nope, 8 there. Sorry about that. I could leave my tick mark in there. 2, 3, 4, 5, 6, 7, 8. 8 on Y, and then 3 times 2 is 6 up. So let's come over here to about right there, and then do 6 up. 1, 2, 3, 4, 5, 6. So there would be the next point. Okay. I just assume not do very many more. Because that's already a pain. Okay. And what it's asking for here is to sketch the path of an object moving along this curve. And then find the velocity and acceleration vectors when t is equal to 1. So let's first do the velocity vector. I always do them first with respect to t, then plug in. What do you have? Velocity vector?
3t squared j.
Right. Oh, yeah, that's I plus 2t 2t squared j plus 3K.
What you said in middle term was?
I'm sorry?
What you said in middle term was? You got I plus what now?
This is R1. That would have, we're taking derivative here. And that,
Derivative.
yeah. And that would be I plus 2t squared J plus 3K. Yeah. Now.
3t squared.
Yeah. Oh, you're right, 3. I couldn't read my writing there, and that's why I was getting, okay, sorry. I can't get my pen to work. There it is. 3t squared, yeah. Okay. Now we won't, let's go on and do the R double prime while we're doing our primes, so we don't forget about it. R double prime of t is what?
0, then 6t.
6tj. And 0 there too. So you only have for your acceleration one-dimensional acceleration, and that is in the j direction. Okay. Now, let's evaluate what they said at t equal 1. Okay. So r prime of 1 would be what? I plus 3j plus 3k. All right. So you have, and this is almost impossible to see in 2 dimensions, but you have one component is coming toward you like this, okay, of your velocity vector. The second component is 3 units that way, and the third component is 3 units up, okay? So it's coming out at you. This thing is, the whole thing is coming at you, so this is coming at sort of a velocity of that, okay? This is v of at 1, okay? And what's your acceleration at 1? So r double prime at 1 would be 6j. Okay? So that means your only acceleration is in this direction. Now, I didn't draw it enough. 1, 2, 3, 4, 5, 6. Really accelerating like crazy in that direction. Your velocity coming to you a little bit in the I direction, moving faster in the J direction and in the K direction, but your acceleration is only in the J direction at that point. So you're not going to change this velocity any or that velocity any. Those two components are going to stay pretty much the same, and it's just going to be increasing this way. So the velocity or acceleration will always be changing, but not, well, sorry, the velocity will always be changing, but these will be small incremental changes. This will be your big change. And that's because you got a t cubed characteristic there. Now, I hate drawing these three-dimensional things. If you'll notice there, they drew the x-axis down this way, the y-axis that way, and the z-axis up. And that gave a lot prettier rendition here, but how do you tell before you look at the problem, or even before you look at their drawing, which is going to be the best way to draw it? You don't know. There's not a clear-cut way that way, but that's why mine looks nothing like theirs, because they've got their whole axis twisted around pretty major there. Okay. So let's make sure we got everything they did. I can't even see where they did what they told them to. It says sketch the path they did on a weird scale, weird axis. Find the velocity and acceleration vectors when t is equal to 1. Oh, there's the velocity vector. Okay, yeah, we got it. I plus 3j plus 3k, and then a is just 6j. Got it. Goodness gracious. What a pain. All right, let's do example 4. Now we're going in a different direction with it. So far in this section, you have concentrated on finding velocity and acceleration by differentiating a position vector. Many practical applications involve the reverse problem, finding the position vector for a given velocity or acceleration. And here is example 4. An object starts from rest. What does that mean? Starts from rest. Okay. In other words, at t is equal to 0, your position vector, well, your velocity vector is 0. Okay? When t is equal to 0, your velocity vector has to be 0, meaning it's at rest when it starts, when t is equal to 0. Okay? At the point 1, 2, 0. Okay, so that gives you your starting position. You're just given, when they say at rest, your starting velocity. This gives you your starting position. Okay? And moves with an acceleration of, so this is your initial velocity. You could write r of t, let's call it r of 0, is equal to I plus 2j, and we'll just leave off the k because there is no k component. I was starting to put 0k, but let's just leave it like that. All right, and your acceleration vector, and moves with an acceleration. An object starts from rest at that point and moves with an acceleration of a of t is equal to j plus 2k. So this is acceleration not at time 0, but at any time t, and that's equal to j plus 2k. But since there is no time component on it, that is its acceleration at time 0 as well. Okay? It's just that's at any time. These are not at any time. You anticipate that you're going, why? You're accelerating. So the velocity's got to be changing. If velocity and acceleration change, these are going to be changing. It's just at time t equals 0, you know what these two are. And you know that one too, but that's good for any time t. Okay. Now, and they're telling us that the acceleration is in feet per second squared. They write it differently, but that's what we usually do. Okay. Find the location of the object after t equal 2 seconds. So we want r of 2. That's what we're looking for. Location of the object at after t equal 2 seconds. So how are we going to do this?
When we started acceleration, Then integrate.
Integrate, exactly. When you're starting at a position, then you differentiate to get velocity's acceleration. When you start at acceleration, integrate to go backwards. So you don't have to do it this way, but this I sort of like this way. A of t is equal to dv dt at t, right? And that's equal to j plus 2k. All right. I'm going to rewrite this in differential form and put my t over there. Okay? Now I'm going to plug in, well, now I'm going to integrate. Integrate both sides of this, and this gives me v of t is equal to what? T j 2t 2t k. Okay? Plus c. Now c is a vector. Okay, remember when we were doing this? If you don't like doing it that way, then I would say write this as 0I plus j plus 2k. Integrate each of those, and then the 0I would just be some constant I plus some other constant, yeah. So you would have a constant in each one of those. So it's either way you want to do it. But we do know that at time t equals 0, the velocity is 0. So v, this is a vector, of 0 is equal to 0. So that means the c sub I is equal to 0. But it doesn't limit what your constant well, I think c sub j also has to be 0 and c sub k. Now I'm putting these in as subscripts here because they've all got to be 0, because this constant, when t is equal to 0, these two are 0, right? And that has to be 0 too, because the whole thing is 0. So that means your ci, your I component of c is 0, your j component of c is 0, and the k component of c is 0. So all three of those are 0. Yeah. So we take this, so this thing is 0 then. And then we rewrite this as dr dt is equal to tj plus 2t k and plus 0, and then do our dt here and integrate both sides, and that gives you r of t is equal to t squared over 2j plus t squared k plus some c, okay? And frankly, I kind of like putting a, let's call this cj, and I wound up doing it anyway, c sub k, and I'm just going to put a ci here as the only one, okay? And that's going to be the vector c, the ci, cj, ci, cj, ck, okay? Well, I'm going to put them with the components, okay? So this one will have an I on it. Okay. Now, our R of 0 is when I put a 0 in for this. We know that the I component's going to be 1. So obviously, Ci is equal to 1. Okay? Your J component, if I can read my writing there, should be 2. Okay? That's when R is equal to 0. So C sub J is 2. And C sub K, sorry, this is 2. And C sub K had better be 0 because I have none. Okay, so this one is 0. So let's write our R. So this is equal to I plus 2J. So we've already done the evaluation. So now let's write down what our R of t is. At any time t is going to be t squared over 2 plus 2. I can't read my writing well, I think that's it. Plus 2, well, wait. Let me get it in right order. Through ijk. I plus t2 over 2 plus 2j plus t squared k, because our C3 was 0. All right. Now, that's what I think it is. Let me just check and make sure that's what it is. V of t equal I. Where is it? There it is. Okay. I plus I'm looking at the wrong one. Oh, looking on the wrong page. That's what hurts. Okay, R of t is equal to I plus t2, t squared over 2 plus 2j plus t squared k. Yeah, that's the answer they got. Now, sit too long, I get really stiff. Okay, if you would take this and take a derivative of it, that just gives you a 0, which is indeed what you've got here. 0i plus tj, there that is, plus 2tk. Yeah, that works out just like we saw it. And R of 0 is equal to I plus 2j. And that's it. I plus 2j. There's your R of 0. Your V of, see if we just did this one, V of 0 would be 0, 0. So sure enough. And it says it was at rest at the initial position. Started from rest. So V of 0 is 0. That's the key. Reading and interpreting at rest means the initial velocity is 0 in every dimension. Okay? So that was key to reading the problem correctly. And then they gave you this one. Initial position was there. And they didn't say anything about it. And just what your acceleration vector was. They didn't say anything about initial acceleration, just what it was, which is held up as a constant, is that forever. So that wasn't t equals 0, but they didn't have to specify that. All right. Kind of a bizarre kind of a problem, but you'll see in the way they work it through here, they did sort of the same thing I did. I just wish at the very first I would have put rather than done a C vector, had done CI, CJ, and CK. I ultimately did it, but it was awkward doing it at that point. they do C1s, 2, 3, 4, 5, 6. You know, keep up with them, and you got it knocked. Okay, how are we doing on time? We've got another 10 to 15 minutes, I think. So let's move on to any questions on that. That's an ugly problem in the writing of it. Sorry about that, but let's go on to projectile motion. All right. There's several assumptions here with projectile motion. It says you have the machinery or the skills or the tools to derive the parametric equations for the path of a projectile. Now, here's the assumption with projectile motion. May or may not be a good assumption, but it's what we assume. Assume that gravity is the only force acting on the projectile. So in other words, the only force on the projectile is downward, straight downward, okay? Now what this is ignoring is wind resistance, air resistance, anything such as that. Coriolis force, anything such as that, we're ignoring completely. The only force acting on it is, after it is launched, is that. Now certainly when you launch the thing, you're exerting an enormous amount of force on it to launch it. But as soon as it leaves the launch pad, the only thing acting on it is gravity. That's what our assumption is. So the motion occurs in a vertical plane. So even though it's three-dimensional motion, the motion is only in 2 dimensions in the vertical plane, which can be represented by XY coordinates if you choose, with the origin as the point on Earth's surface down here. So if you had an initial height up here, and they didn't tell you what it was, let's just call it H, because it's not A, that's your acceleration down, okay? Your initial height here, then it's going up in a parabolic curve and come back down and hit the ground here, okay? Now, the other thing that you're told is what your initial velocity is, okay? Whatever it happens to be, usually is 2-dimensional, an X component and a Y component. If there's only a Y component, then the motion is straight up and straight down. It's a linear motion then, not a 2-dimensional motion, it's a 1-dimensional motion then, up and then down. If your initial velocity were horizontal, you still got 2-dimensional motion because gravity is pulling you down. So, and if you fired it down, you'd have 2-dimensional motion, up 2-dimensional motion. So whatever you do, unless you fire it straight up, you have 2-dimensional motion. Okay. Now, we're going to break that into pieces later. They're not doing it yet, which is a shame, because they're just drawing in derivatives, which is fine. That's all we're doing at this point. But your initial velocity, you start with an initial height here. Okay, that's just given. Initial position, so many K. Or we'll call it J here. So many J up here. Your acceleration due to gravity is constant on the Earth. Okay? And that's what your A is here, and I haven't told you that yet, but that's what it will be. Typically 9.80 meters per second squared, or 32 or 32.2 feet per second squared. If you use other units, you deal with that. If you are on another planet or the moon, you deal with that. You have a different acceleration. But anywhere on the surface of the Earth, that's going to be a constant. Or on any other planet, it will be a constant, just a different constant. Okay. Your initial velocity, of course, has to be tangent to the initial position, to that curve at its initial position. Now, what they don't tell you is that the X component does not change. The Y component changes because your acceleration is downward. But this downward acceleration does nothing to your X component. So your X component is staying here, as it is here, as it is there. X component does not change. The Y component is constantly changing. It was pretty steep here, a lot less steep here, and now actually it's negative there. Well, you get that by just looking at the tangent lines here. Okay? That's fine. What you don't know is how long to make those until, well, you don't know how long to make them. Okay? So they've drawn them in the length they think they ought to be. It's not the same as this. That's getting shorter. This should be getting longer. That's going to be near its minimum speed. And that looks like it's about the same speed as that, which is not a fair representation. This should be longer than that. And perhaps it is, but just a little bit. It should be a lot more. See, that's considerably longer. This should be almost as long as this one. So they don't have that quite right, but the acceleration is right. Okay. For a projectile of mass m, the force due to gravity is minus mgj. Always downward. Always in toward the center of the earth. It's always along the y-axis. Okay? There's always a minus on there. Force due to gravity. For the acceleration due to gravity is this g. And they use 32 feet per second squared or 9.8 meters per second squared. By Newton's second law of motion, that same force produces an acceleration. A is equal to a of t. So that's going to be your a of t. Whether you use 32 or 9.8, whatever you use, that satisfies the equation F equal ma. Consequently, the acceleration of the projectile is given by ma is equal to m minus mgj. That's this and that. You just put in a is here and minus mg here. The m's cancel out, so it implies that a is equal to minus g. Acceleration due to gravity is always negative 32 to 9.8, whatever unit you're using. Okay, always. Okay. Here's example 5. Do we have time for it? I think it's fairly short. Let's see. Projectile of mass m is launched from an initial position r0 with an initial velocity v0. Find its position vector as a function of time. Okay? So what we're looking for is r of t. Okay? Now they give us an initial position and they give us a initial velocity. Find its position vector as a function of time. What is the thing they haven't told us? Say again?
Your position.
Okay, yeah, that's what we're looking for. They mentioned something about velocity, something about position. What are they missing?
We're going to do an angle or we're going to do acceleration?
Yes, it's acceleration we're looking for. What is the acceleration? They just told us. Acceleration vector is equal to, just told us, minus GJ. Minus GJ. For every projectile motion problem, that's your acceleration. Now, we're dealing just two dimensions because your motion is in a plane, so we can use the vertical of that plane to be J and the horizontal of that plane to be X. Okay? So, can you tell me what this is the same as dV dt? So, write that in differential form, dt, and integrate both sides. Just forget about the a in the middle. This gives you v as a function of time is equal to, yeah. Now, I'm going to do something else I wish I had done on the last one. I said I could do it that way. I wish I had done it that way. 0I minus g j dt. Okay? So, what is your velocity as a function of time then?
0I.
I would say C1I, because the derivative of a constant is, I said I and wrote T. There's something wrong with the brain here. C1I. I put CI. Let's do C1 just to keep the I's from being so confusing. Let's call that C1I. That's what the book uses. Okay. C1I. Next. Minus GT plus C2J. Isn't that all right to do? Because you would have a constant there too, right? All right. Now, we know the initial velocity, V0, that means when t is equal to 0, V of 0 would then be C1I plus C2J. That's your V0. We'll just name it that, C1I plus C2J. Because when t is equal to 0, that doesn't contribute. Okay? Now, I guess we could have done that here too. C1I plus C2J, and named this to be, oh, I'm sorry. This is our C1I plus C2J, and name that C3 and C4. Okay, sorry. Okay. Now, so your velocity vector is that. Okay? This is dr dt. Write it in differential form. Okay? Integrate both sides, and you get r of t is equal to you can write C1Ti plus C2Tj, and that would just be simply V0, because that's what your V0 is, times T. Okay? That's when you integrate those two, and this will be minus G T squared over 2, right? J. All right, because that was part of your J vector. Okay, plus a C3I plus C4J. That's your initial vector there. So your R as a function of time is R0 plus V0t minus 1/2 GT squared J. I just wrote it backwards from what they did. But that's typically your position vector. They write this one first, minus 1/2 GT squared J plus VT V0I plus R0. And that is your standard way of doing it. Now, what we're going to do next, and we don't have time today, but what we're going to do next, oh, let's see, I forgot they're doing it too. So let's just see, sorry. All right, begin with that, exactly where we began. Integrate twice, and they put in the capital C's now. I probably should have done it that way this time, but that just gives you G minus GTJ plus your C1. That C1 is just your V0, okay? Then the RT, when you integrate that, you get the second one. And if you name this V0, which is exactly what it is, because that is a 0, that was your V0, and put that in, then the C2 becomes your R0. That one up there, okay? And that's what they get here. V0 is equal to V0, R0 is equal to R0, and that's exactly what you get there. So minus 1/2 GT squared J plus T V0 plus R0. Now we'll start here next time. This is the bottom of, I'm going to do it with my pencil. Well, once upon a time I had a pencil up here and now I don't. So I'll find me another pencil. I did go digging through my drawer here, so I guess I may have carried it. All right, we'll begin there next time. I forgot to bring up my eraser today, so I don't have much of an eraser here. Now, homework exercises here. Whoa, we came close to finishing. Any of the odds 3 through 9, they're all at Calc Chat, 3's at Calc View. Any of the odds 11 through 19, they're all at Calc Chat. 15's at Calc View. Any of the odds 21 to 25, they're all at Calc Chat. 21's at Calc View. And we'll save the rest of those till next time. Okay. I wonder what I did with my pencil. All right, any questions? Sorry, that got a little long at the end.